More frequently, you are comparing means based on independent samples. This only means that the groups are different. For example, you might be interested in comparing satisfaction rates between experts and novice participants. The most common question is whether the two groups are different. For doing this, we can use the independent samples t-test. Usually, when the test is simply called as a t-test, it always indicates the independent samples t-test. In other words, when your method is the one sample t-test or paired samples t-test, you should mention the name exactly. So the independent samples t-test are used to compare mean scores of two different or independent samples. Therefore, the size of both samples are different. They could be the same by accident, but perhaps they are mostly different. In introduction video, an example was introduced. The mean height of data of two independent groups were compared. The first 26 people belong to the freshman group, and the other 26 people belong to the senior group. When we draw the two distributions, it might appear in this way. The mean and standard deviation and the size of samples are displayed in this table. In case of the independent samples t-test, the calculation of t looks a little bit more complicated. You don't need to memorize the formula. You should use your brilliant brain to generate creative ideas. That's what I'm thinking. But it looks like this. Here, the numerator is just a subtraction between, or the difference between two mean scores. However, the denominator adopts the pooled standard deviation, and this pooled standard deviation is called in Korean 합동 표준 편차. And then you get the degree of freedom by adding the size of sample 1 and size of sample 2, and then you subtract 2 from the sum. Using this formula, of course, you can calculate the t-value, but you can more easily perform this independent t-test in Excel. So again, I already prepared for you 26 data of freshmen and 26 data of senior students. And here you click data analysis and the t-test, and here we assume equal variance. So we assume this equal dispersion of the data of each group. So here, and we assign the first range and then second range to compare. And the first row is considered as a label, so I clicked here, and our alpha level is usually set 0.05. And my output will start from this cell. Click. Okay, here you go. So it's very quick and easy. So the mean was calculated. In fact, we don't need such a long decimal point. So for us to see a more compact number, which look more beautiful, okay? Mean values and sample variances, and then the size of sample 1, size of sample 2. By accident, in this case, the sizes are identical. and the pooled variance is like this. If you remember the procedure of calculating the pooled variance or pooled standard deviation in a PowerPoint slide, this Excel function will reduce a lot of your time. Okay, and here the t value, we view here the two-tailed because our focus is to see or to examine whether the mean of this height is different from the mean of this height. So in this case, we are not saying which group is taller than the other. So our interest is to identify, to statistically test whether there is a statistical difference or not. So we better view the two-tailed result. The critical two-tailed value is 2.01. So let's move to distribution, and this is the t-distribution, and the degree of freedom is 50, and in two-tailed case 2.01, right? And if I see the left tail or right tail or left tail, then the value is, the absolute value is suddenly increased because we, in the right tail situation, we only can consider the right side. So therefore, the threshold of a t-value is decreased from 2.1009 to 1.676. Okay, so the t-critical value or the threshold value is 2.01 in case of a two-tailed comparison, and our t-value is 0.72. Therefore, and our t-score is minus 0.36. So this is far smaller than this value in terms of absolute value. Therefore, we cannot conclude that the mean differences are statistically significant. So in the text, we should write that the mean heights of both groups are statistically identical or statistically not different. Using the SPSS, of course, you can perform the independence t-test. In SPSS, please be aware that you should give the data in this way. So the one column is identifying where each height score is belonging to. So you need two columns. One is for the membership of the data, and the second column, second variable, is actually the height. And then you click Analysis, Mean Comparison, Independent t-test. You give height as the variable to compare, and here this is the group distinction, and we 1 to 2 because freshman is coded as 1 and senior is coded as 2. Therefore, I gave 1 and 2 to compare, and then press. All right. So here is the result, and it says that the t-value is minus 0.36, identical from the Excel result, and the probability is 0.719. It is a lot greater than 0.05. So the mean difference of two groups are not statistically significant. The difference of the mean difference is still within the tolerance. That's should be the conclusion. When our interest is to examine the mean difference, we are considering the two-tailed test. In SPSS, by default, the t-test is set for the two-tailed test. However, when our interest is to examine whether seniors are bigger than freshmen, we can take the one-tailed test. Before we perform the t-test, it is already known that the seniors are bigger than freshmen because this number is bigger than this. So we can consult the t-distribution only focusing on the left tail. The numerator is 1 meter 68.70 minus 1.6904. So it will be a negative value. When we find the t-score in the t-distribution with the degree of freedom of 50, it is actually minus 1.676 when degree of freedom is 50. This is the t-distribution. With this data, we already know that the t-score was calculated as minus 0.36 with this data, and which is anyway much smaller than this. So our t-value is positioned somewhere here. But suppose that we would have the t-value such as minus 1.8 like this, and minus 1.8 is less than minus 1.676, but it is bigger than minus 2.10 or 0.1. I think it was 0.1, right? Minus 2.01 is the threshold value of a two-tailed case. In this case, depending on how many tails we take into consideration, the conclusion may differ. Also, with one-tailed test, with a smaller mean difference, we can easily reach the threshold. In other words, in order to obtain the statistical significance with a two-tailed test, we need larger mean difference than with the one-tailed test. Therefore, that is the reason why the two-tailed test is for a more scientific and stringent study.